Hello, everyone. If anyone is whatever device you're in, we're going to do our best to mute people proactively from within the system, but it'll really help the quality of the call if you can mute your own device. I'm Josh Jacobs. I'm the Director of Operations and Program Integration for Leaders for Global Operations. Today's webinar is with Dr. Stanley Gershwin from the MIT Lab for Manufacturing Productivity. Just very briefly, as you saw in the message that went out, Dr. Gershwin is a senior research scientist at the MIT Department of Mechanical Engineering, and as I said, a member of the Laboratory for Manufacturing and Productivity. He's had research positions at Bell Labs, Draper Lab, Laboratory for Information and Decision Systems, and was a professor of manufacturing engineering at Boston University. He's the author of Manufacturing Systems Engineering and many papers in international journals. He's an active advisor of LGO and SDM students, where he and his students have done research in such companies as Boeing, GM, Polaroid, Johnson & Johnson, and others. He teaches a couple of courses that our students typically take, including Introduction to Manufacturing and Systems, and he's a graduate of Columbia and of Harvard. So as I've been saying in the chat, we're going to start the seminar now. Dr. Gershwin's going to talk for perhaps 30 or 40 minutes. During his talk, if you don't mind signaling to me that you'd like to ask a question using the chat, he's happy to take your questions along the way. And I see Andy Storm has a question already. Andy, do you want to tell me what it is right now, or can it wait? Okay, you're in the queue to get the first question as of now. All right, thanks everyone for joining, and here's Dr. Gershwin.
Hello. Good to talk to everybody. I'm going to be talking, as you can see, about inventory and variability today. So, we all know that we don't like inventory, and I'll remind you of why, and we do our best to do without it. However, variability makes inventory necessary, and we don't like inventory, we certainly don't like variability. And what I would like to do today is to describe the relationship in general terms with some examples about the relationship between variability and inventory. First of all, why don't we like inventory? It's got heavy costs. We have to pay for raw materials early, and we don't get revenue until much later when we sell the product. There's demand risk, reasons why products won't be sold. All LFM and LGO students know all about the news vendor problem. And the longer an item is in storage, the more likely that one of these bad things are going to happen. Other costs include holding costs, damage, theft, loss, otherwise known as shrinkage, reduction of yield when inspection is not immediate. If you don't inspect a product until several buffers down the line, then you'll have a whole pipeline full of bad parts before you're able to repair the problem. And of course, inventory often can conceal the causes of problems, the problems being the sources of variability. On the other hand, there must be some reason why people have inventory, and that's here. Basically, the purpose of storage is to allow systems to survive even when important events are unsynchronized. Storage improves system performance by decoupling parts of the system from one another. Important events are unsynchronized, such as the production of something and the need for that thing. Those are not synchronized generally, and one or both of them occurs at random times sometimes, so something has to get stored in between, and that random time is the variability. Storage reduces the propagation of disturbances and thus reduces the instability and the fragility of complex, expensive systems. And storage allows production systems to be built with capacity less than peak demand. And in particular, when the electric part of our economy becomes more and more solar-based or wind-based, we're going to have to think very hard about storage because the sun doesn't shine at the same time that we need the energy from it. It reduces the propagation of disturbances. It allows economies of scale, either due to volume purchasing or reduction of, reduction of the frequency of setup changes. It helps manage seasonality and manage limited capacity. And it helps manage uncertainty. Short-term uncertainty includes random arrivals of customers or orders, and long-term is the total demand for a product for the next year. So let's talk about variability then. Variability has lots of random causes, such as random demand, random or unreliable suppliers, machine failures, human variability, and I'm sure you can think of a lot of others. There are deterministic reasons why we have variability, such as setup changes or setup costs. Setup changes have costs associated with them and also times associated with them. And if we allow setups too often, we lose capacity and spend money. But if we have setups too frequently, if we have setups too infrequently, then we get inventory. There are also machines that are batch-oriented, such as ovens. There are ordering costs and MRP nervousness, which occurs when you reschedule a system that's controlled by something like MRP, and a small change in requirements can lead to a big change in the schedule. Okay, so now let's talk about how variability causes inventory. And I'm going to show you this with a bunch of tanks and water and pipes and so on. So this first slide shows a system with no variability. We have a small pipe on the left in which water is entering, and it is completely full. We're using that pipe at its capacity. However, so the water goes into buffer 1 and leaves buffer 1 by a larger pipe, and then goes into buffer 2 and leaves buffer 2 by a larger pipe. So the bottleneck in the system is the small pipe, but there's no variability in the system. So water enters buffer 1 and leaves it at the same rate, which means that buffer 1 basically stays empty all the time, except for, a small puddle on the bottom. The water flows out of buffer 1 by that large pipe and enters buffer 2, and the same thing, it's entering buffer 2 at the same rate that it flowed in through the small pipe. And I've put these little flow meters there just to emphasize this. So the water is flowing through the whole system, the buffers are empty, pretty much, and the rate of flow out of the water equals, out of the last pipe equals the rate of flow into the first pipe. And this never changes because I'm assuming no variability. So there's no failures, no interruptions, and so on. So this is my no variability example, and I want to call that case 1. Notice, just to get ahead of myself a little bit, you can see that the buffers are really not doing us any good. We could make them much, much smaller or much, much bigger, and it wouldn't change anything. Okay, now for case 2, I need a lot of slides. Not all that I could possibly want. Anyway, case 2 is one where there is variability, and the variability occurs in these valves that I've put in the pipes. At this point, all the pipes have the same size. So when water is flowing, it could flow at a greater rate than in case 1. Okay? Right now, in this figure, all the pipes are closed. So the level of water in tank 1 and the level of water in tank 2 are the same. They never change. And the flow rate through the system is 0. Okay? But it doesn't stay this way all the time. In particular, let's open valve number 2. Okay? The middle of the valve between the two of them. Now, when we do this, water flows from buffer 1 to buffer 2. Notice we haven't opened valve 1 or valve 3, so the flow in those valves is 0. In those pipes is 0, but the flow of water in pipe number 2, in the pipe between buffer 1 and buffer 2, that's at 100%. That's going as fast as it can. Now, if the valves stay in this state indefinitely, then eventually either buffer 1 becomes empty or buffer 2 becomes full. And when that happens, the flow stops. Okay? And now you can see that the buffers are actually doing something. They're allowing flow to take place even though some of the valves are closed. Okay. Here's a case where valve 1 is open and valve 1 is closed, and we've opened valve 2 and valve 3. Now, in that case, tank 1 is emptying. Tank 2 stays constant until tank 1 gets completely empty, and then it becomes empty. It loses water, but until that happens, it stays constant. But I'm looking at it before tank 1 becomes empty. So you can see that the flow rate into the system is 0. But the two other valves are allowing the water to go through their pipes at the maximum possible rate. Okay. So here's another case. In this case, I've closed. This is not following the previous one. This is just at some later time. In this case, I've allowed valve 3 to be closed. And valves 1 and 2 are both open. But I've waited a long time before showing you this picture, and what happened was that both buffers filled up. So now we're in a situation where we're blocked. No water can flow from buffer 1 to buffer 2 because buffer 2 is full, and no water can flow from the first pipe into buffer 1 because buffer 1 is full. So nothing happens here. So even though the two upstream valves are open, the flow through them is still 0. Okay. Now, the thing that I want to point out here is that we had no inventory, no variability in case 1. In case 1, where we had a constant flow through the system, there's no flow. There's plenty of flow, but there's no variability, and there's no accumulation in buffers at any time. However, because of the variability in the 3 valves, sometimes there is inventory in buffer 1 and buffer 2. Now, let's think of these as the valves as machines which are unreliable. And we'll characterize the valves. The time that they're open, we'll think about that as a mean time to fail, and characterize the times that they're closed as mean time to repair. So the valve open meaning that we have a working machine, and valve closed meaning we have a down machine. Well, I will claim that for this situation, for some set of parameters of mean time to fail and mean time to repairs for these valves, the average flow rate of case 2 is the same as the flow rate of case 1 for some set, okay? But what's the difference? The difference is that even though the averages are the same, we have variability in the flow, and as a consequence, we get inventory. Okay, like it or not, there's inventory in that case. So the conclusion is that variability causes inventory, because the tanks in case 1 are always empty. The tanks in case 2 gain or lose materials due to the unsynchronized valve behavior. Okay. Furthermore, variability makes the inventory necessary. We would get exactly the same flow in case 1 if the tanks were not there, Whereas in case 2, the flow rate, the average flow rate, depends on the valve behavior and the sizes of the tanks. And if, in order to make the average flow rate of case 2 the same as the flow rate of case 1, we need tanks. We must have tanks. If we had no tanks, and we had no buffers in case 2, we would still get flow when all 3 valves are simultaneously open, but that might not happen very often depending upon the parameters that we have, and it might not happen often enough so that the average flow is what we need it to be. So therefore, under some conditions, the variability makes the inventory necessary. If there's enough variability, then we must have inventory in order to meet targets. So that was pretty abstract. Let's get even more abstract just for a moment. I want to take a very general abstract view of what a manufacturing operation is. For an operation, well, clearly the goal of the operation is to take that part on the left and do something to it and send it out on the right and make it closer to what you can finally sell. So you've added value to it. But in order for that to happen, not only do you need the part, you need other things. You may need some consumable materials such as chemicals or cooling fluid. You generally need a machine. You often need an operator. But then also you need some place to put the part after you've completed it. Otherwise, the operation can't take place if that machine is blocked, if it's got no place, no downstream machine that's available or no place to store the part. In addition, we have to take the waste away, and the waste system could get full or it could be unreliable and so on. So the point is that in order for this operation to take place, everything has to happen simultaneously. Nothing happens until everything is present. Well, it would be nice to think of factories as operating like clockwork, but they don't. And so frequently, not everything is present at the same time. And that leads to waiting, which is a sort of generalization of the concept of inventory. In general, whatever does not arrive last has to wait. So, for different things waiting, we have different names. Inventory is what happens when parts are waiting. Underutilization, capital underutilization, is occurring when machines are waiting, and we get an idle workforce if operators are waiting. Okay, so again, the relationship between the things that are moving around in the factory and the things that stay constant, when there's variability, we lose something. In particular, if the availability of the items we need is reduced, or if we get variability in that availability, then that causes waiting in the rest of the items and reduces the performance of the system. And therefore, in order to get the target performance that we need, we may have to add something extra to the system. So, variability has lots of reasons for its creation, and I'm trying to list them over here. I'm repeating myself a little bit: the random demand and supply and machine failures and so forth. And there are cures for those things. You can better manage demand, you can find more reliable suppliers, improve machines, and so on. Okay, so that's the creation of variability. There's also blockage there's propagation of variability. So a failure of one machine can cause some other machine to be idle, can cause some other machine to stop. In the case of the tanks and the valves, closing down the third valve eventually caused all the flow to stop, so nothing was going through the other two valves. So the propagation is really blockage and starvation. We block the upstream part of the system, or we starve the downstream part of the system. And the cure for that is inventory. Now this is propagation. Of course, to reduce the creation of variability, that's the business of the previous slide. And finally, variability can be amplified in manufacturing and other kinds of systems. As I mentioned before, MRP nervousness occurs when a change in a schedule occurs due to a change in demand or something else. And mostly the issue that causes the nervousness is the batching. The cure is to reduce setup and ordering cost, which means we can get by with smaller batches, or to develop improved scheduling methods. So, to summarize all this, factories should be designed and operated to minimize the creation, propagation, and amplification, in fact, of uncertainty, variability, and randomness. And if you count them all, I think there's something like 18 different sentences going on in there. Let's talk about a little bit more variability. Here I've got flow through a buffer, and I've got machines that are unreliable. And the difference between the two cases on this slide is that the machine on the left has a small buffer. If you can read the vertical axis, the size of the buffer is 10. That's the maximum value there. In the case on the right, the size of the buffer is 100. Also, I should point out that the picture on the right has a time scale that goes up to 10,000, whereas the one on the left only goes up to 1,000. So that accounts for some of the difference in the appearance. But the important thing here is that when the buffer is small and the machines are the same, we frequently fill up or empty the buffers. Okay, and filling up and emptying the buffer is what causes the propagation of variability. The case on the right, we can see that there are many events that are taking place. All these zigzags up and down are due to failures and repairs of the two different machines. When the upstream machine is up and the downstream machine is down, the buffer level line goes up, and vice versa, the buffer level line goes down. And when they're both up or both down, then it's flat. And you can see that there's a lot of events that are taking place here. However, the buffer is very rarely full, which means that machine 1 is not very often affecting whether machine 2 can operate, and machine 2 does not very often affect whether machine 1 operates. Whereas in the case on the left, it happens much more often. Now, for these graphs, I've changed one of the machines, and I've made it worse than the other one. And you can see that on the picture on the left, machine 1 fails more often. I've cut its mean time to fail by half, by 2. So what happens here is that the buffer is frequently empty, but never ever full. If I went for a longer time, it would be full sometime. But you can see that times of blockage are very, very rare. So just from looking at this graph, we can see that we're wasting a lot of buffer space. We could cut this buffer down to about 50, and it wouldn't make very much difference in the performance of the system. So we're wasting all that space. We're not wasting so much inventory, but we're wasting an awful lot of space in the buffer here because we very rarely use the buffer. We use all of it, okay? On the other hand, the machine on the right, the graph on the right is where I've reversed the line, and now the second machine is the bottleneck. So it's just the reverse case of the one on the left. And now you can see that the buffer is full quite frequently and hardly ever empty. Okay? Now, you might think that this tells us that we need a very small buffer for the case on the left to get a certain performance, and a very large buffer for the case on the right to get the same performance. But in fact, I will argue that's not true. And in fact, we need the same size buffer in both cases to get the same performance. So let's talk about that. This is a graph of the production rate of the system as a function of the buffer size. And you can see some interesting behavior. First of all, when the buffer size is 0, the production rate does not go to 0. It goes to some larger value. But as the buffer size increases, the production rate increases, but it increases first steeply and then not so steeply. So if you were going to ask what would be the optimal size of the buffer for this system, I would say, if you can read the numbers on the bottom, that it's somewhere in the neighborhood of 40. Of course, depending upon lots of circumstances. Basically, if you had a buffer of size 200 and you reduced that to 160, you would make hardly any change in the production rate of the system. On the other hand, if the buffer was 5 and you raised it to 10, you can see that that would make a big change. So therefore, we don't want a very big buffer, because a small reduction will not hurt the performance, and we probably don't want a very small buffer, because a small increase will increase the production rate a lot. So that means that probably the optimum lies somewhere around the knee of the curve, the curviest part of the curve. The other thing that you can't see from this picture is that I would get exactly the same graph, if I turned the line around, if I reversed it. So I can, this could be in particular, this was for a 2-machine, 1-buffer line. But if it was even for a 10-machine, 9-buffer line, the graph would be the same if I took that line and just simply reversed it. Gave machine 1 the reliability characteristics of machine 10, gave machine 10 the reliability characteristics of machine 1, and so forth. The production rate would be exactly the same. So, it does not depend on the sequence of the machines. It only depends on the characteristics of the machines. So, let's go further. Now, this graph looks at inventory versus buffer size for the same kind of system. And now you can see that the amount of material in the buffer on the average depends on the location of the bottleneck. If the bottleneck is at the first machine, the buffer level stays very low. And even if the buffer was infinite, we would still have a finite average buffer level, a finite average inventory in the system. On the other hand, the red graph, the bottleneck is at the second machine. And if we make the buffer bigger and bigger, then we get more and more material in the buffer. And if we had an infinite buffer, we'd have an infinite amount of material there. But what I'm asserting is that for either one of those graphs, if they're a result of the same line but switched from front to back, the production rate versus the buffer size is exactly the same. So therefore, if we have our choice, we certainly want to put the bottleneck at the first machine. So let me go back to this then. If we look at this graph, if you look at the graph on the right, what's really going on here, the reason why I'm claiming that that buffer could have been reduced to the same amount as we reduced the size of the buffer on the left, is that all of the variability, almost all of the variability, they're not quite mirror images of each other, but the variability in the buffer level occurs for buffer levels over about 60. It very rarely gets below 60. So if I took out 40 spaces from that buffer, most of the time it wouldn't make much difference, okay? Except that I would have 40 fewer parts stored in that system. So that's the reason why this graph is not a function of the order of the machines, at least in a 2-machine line. Okay, let's look at this one. Now, I'm going to go through 4 graphs that are going to look roughly like this. This one and the third one show average inventory in the systems, and my color code is that's red. For the second and the fourth, I'm going to talk about the optimal amount of buffer space. So here's what I'm trying to do. In the first one, I've decided that I have a line. You can see that it's 20 machines. What the graph is about, the horizontal axis, it indicates the locations of buffers, and the vertical axis indicates the average inventory in those buffers, okay? So for the first case, all the buffer sizes are 23. So why 23? Because I wanted to have the production rates of all of these 4 cases to be the same, which is 0.88, and that was as close as I can get. Okay. Now, the reason for the shape has to do with the fact that we always, in looking at these cases, assume that the first machine is never starved and the last one is never blocked. It essentially becomes a lot harder to get material out of an upstream buffer because of all the downstream machines that could block it, and a lot easier to get material out of the downstream part of the line because it has less downstream, and then vice versa. It's harder to get material into the last buffer because of all the machines that are failing and possibly starving that. So we get that shape. Okay. Now, suppose I asked another question. The question is that I'd like to optimize the distribution of buffers. I want to minimize the total buffer space that I need in order to get the production rate of 0.88. Okay. Now, I always trap my students when I show this picture because almost everybody says, well, the first buffer ought to be bigger and the last buffer can be smaller. It's clear the last buffer can be a lot smaller because on the average it only has about 6 or 7 parts. We certainly don't need a size 23. We could probably get by with a size 10 or 15 or something because it will hardly ever get to be to have as many as 10 parts in it. Well, let's optimize. Okay, so there's the optimum. We got the production rate almost the same. The blue bars represent the optimal buffer sizes. Now, this looks surprising because not only are the buffers on the back end of the line, the downstream end of the line, smaller than the middle, but the ones on the upstream end of the line are also smaller. And that seems very surprising because it seems as though we need more space because we get more material in there. But the reason for that is that in both the very far upstream, let's go back to this one, in the very far upstream machine and upstream buffer and the very far downstream buffer, there's the same amount of variability. It just happens that in the first one, the variability takes place between around 10 and 23, and the last one takes place between around 0 and about 13. So we certainly can remove a lot of the space of the last one, but we can also remove a lot of the space of the first one because the buffer is only there for variability, not just to store things. And one way to think about this is that let's suppose that the parts were going into that first buffer, not first in, first out, which we're all implicitly assuming, but last in, first out. Okay? If they were going in last in, first out, then let's say those first 10 parts, the bottom 10 parts in that buffer, probably, once they get in there, will not leave for a very long time because that buffer is not going to go to 0 very often. Which means that those bottom 10 parts are doing nothing for us. And if we replace them with bricks, we would get pretty much the same performance. So let's just get rid of those bottom 10 parts and let's get rid of those bricks. And so we have this picture. Okay. Now for the next one, I've now caused some problems. Oh, I didn't say it clearly. The first 2 cases, I had all the machines the same. In this case, I've given myself a bottleneck, and the bottleneck occurs at machine 5. Okay? And this, again, is the distribution of inventory. And in order to get that same production rate of 0.88, I had to increase my buffer sizes to 37. Well, that's not so surprising because that bottleneck is preventing flow. So to compensate for that bottleneck, I have to increase my buffer sizes, and I've chosen here to have the buffer sizes all the same. So now, in order to get that 0.88, I need a total buffer space of 703. I need 703 spaces because it's 37 times 19. Okay, but now when I optimize, I get this interesting picture. The blue lines now are not average buffer levels, they're the optimal sizes. Again, I've managed to get a production rate of 0.88, but now I've managed to do this with a buffer space of only 510 spaces rather than 703. Okay, well, why is that? Well, clearly at the downstream end of the line, I don't need, in other words, or rather everything south of the bottleneck, I don't need very much space at all. Those buffers are empty most of the time, or rather non-full almost all the time, so I can certainly cut them down. But as you can see, I'm also reducing the size of the first couple of buffers, and the reason is, again, the same reason. Now the variability in those first few buffers is also similar to the variability in the last couple of buffers, and so therefore we need the same size. We don't need large buffers. We've put very large buffers, buffers of size 50, 51, 52, in the neighborhood of the bottleneck, because that's where we need it, and we get a little bit of benefit by putting it close by. But we don't get very much benefit by putting much buffer space far away from the bottleneck. So the conclusion is that buffer space is not needed where inventory is greatest. Buffer space is needed where inventory variability is greatest. And that pretty much completes the talk. The point is that variability causes inventory, and inventory is there to try to ameliorate some of the effects of variability. Okay, I can take any questions, if there are any.
Thanks a lot for that. You can just signal to me. Everyone's muted for now, so if you've got a question, please just signal in chat. Andy Storm, do you want to be the first?
I guess not.
Guess not. Okay. Not seeing any hands. Okay, Chris Harper, go for it. They're unmuted. And okay. Chris, it looks like you need to call in either using the computer audio or your phone.
Or you can send in a question by chat, no?
Yeah, that's right. Send in a question by chat if you like, and we can just do it that style.
Can't see. What would you read it out loud?
Oh, sure. Okay, Chris Harper asks, what is the tool you're using to determine the optimization? What is the simulation tool? That's the product of some research we've done. That's not simulation. Well, first of all, there's two issues. The first issue is how do we even evaluate lines like this? And we're not evaluating them by simulation. We're evaluating them by approximate analytical methods, which work very well. We've done extensive comparisons with simulation. And once we knew how to evaluate the line, we then developed some analytical optimization techniques, and we're still developing it. So that's where the optimization came from. But it was not from simulation. Okay. Someone asks, is this the goal all over again?
I don't think so. I mean, for one thing, we've got analytical tools that we can use to do all this analysis. I found the goal to be correct as far as it went, but it seemed to be a little vague. And in particular, I think that if you look at this slide, I think that Goldratt advocates putting, somebody, I think it was Goldratt, advocated putting a lot of buffer space upstream of the bottleneck so that it would never get starved, but there was no discussion about putting inventory space downstream, symmetrically about the bottleneck. But our optimization, and then after all, you know, we thought about it a lot, and it makes a lot of sense that it should look like this. So just starving the bottleneck, just preventing the bottleneck from starvation is not enough. You also have to prevent it from being blocked as well. I think the difference between the goal and this is that the goals, the Goldrat's methods, as far as this goes, to my knowledge, I don't think he described them in any detail, were mainly qualitative. Whereas we can go a little further than that with a little bit of mathematical analysis.
Any other questions? Did those answer your question? Okay, here's another one. Tyler Hooper, how is optimal inventory buffer impacted by a high degree of variability in demand?
Well, the in-process inventory, as well as the finished goods inventory, are there to keep demand satisfied when either demand increases in a random way or something happens upstream. Now, one thing I should say is that the sizes of the buffers, then that includes finished goods buffers, should be consistent with the size of the variability. In other words, if the demand is only changes by a few percent, then you can probably get away from one day to the next. You can probably get away with a pretty small buffer. But if the demand swings wildly, then you need a buffer that's large enough to accommodate those swings. And in particular, the extreme case of this is seasonality. When you start producing for the Christmas season in August or July, you're just creating a huge buffer because of the huge variability in demand, which you're going to satisfy when Christmas rolls around.
Follow-up question from that same person. Is this your safety stock part of the ROP equation?
Yes, that's one way of looking at it, except that I think that, first of all, the lesson that I wanted to get across here is the relationship in general between variability and inventory. I wasn't looking at quite the same problems, but basically it's closely related.
Have you considered scenarios where the, quote, cost of buffer space is not the same at each step in the process? How does that change the optimization?
Yes, we've looked at that, and you know, it changes it the way you would expect. You would try to reduce buffer space where buffer space is expensive. A very good example of that is where you have a clean room, and anything that goes on in the clean room is expensive, including allocating some of the clean room space to storage, and any kind of special environment, such as a refrigerated environment. So yeah, when that cost is high, you're going to try to get by with a little of that as possible, and that's what our optimization show us.
Just as a lay person, Stan, I wonder if you could talk about any particular actual company scenarios where you've drawn inspiration for this work or seen it applied.
Well, we had an experience actually quite a while ago now. One of my students advised Hewlett-Packard, when they were starting to produce inkjet printers, they attempted to get by essentially with zero buffering, and they discovered that they were going to fall far short of the target production rate that we needed. And he was able to show them, in fact, let's go back to this graph. He was able to show them that with a relatively small amount of buffer space, they could achieve close to their targets. They didn't need to have very large buffers. They were able to get by with very small buffers. But if you have an absolute prohibition against buffers, you're going to have buffers of size 0, and it'll make it much harder to achieve production rate targets. Whereas what this graph shows is that a relatively small amount of buffer space can make a big difference in the production. General Motors has developed similar techniques, and they have done a lot of their production design of factories this way. I should say that HP case and the General Motors case, and one more that I'll tell you about, were Edelman competition finalists or winners. The GM case was a winner. Citroën Peugeot was doing the same thing. Peugeot was doing something like that as well, designing factories, designing automobile factories using these kinds of ideas.
Okay, any further questions?
Maybe everybody wants lunch who hasn't been eating their lunch at their desk.
All right, as I mentioned in chat, this has been recorded so that you and other LGO STM people in the community can access it later on. I'd like to thank Dr. Gershwin for participating in the call today. And a reminder to please send me your suggestions for other MIT folks or others who you'd like to see featured in the upcoming webinars in the spring semester. So thanks to everyone for participating. Please feel free to send me feedback at jsjacobs@mit.edu, and hope you all have a good week. Thanks a lot.